So here was the third question from the exam. And on this question, you're supposed to prove that the null space of a matrix or a linear transformation, I guess it's a matrix in this example, prove that the null space of that matrix is a vector subspace. There were some typos on here, so let me make sure I get those fixed. If A is an m by n, so m rows and n columns matrix, then the null space is going to be a subspace not of Rm as it was written, but rather of Rn. So I had you fix this on the exam as a typo. And so the question was to prove that this set, the null space of A, which is defined for you here in the problem as the set of all vectors x in Rn, such that A times that vector x is equal to the 0 vector. And you're supposed to prove that that set is a vector subspace of Rn. So beginning from that, what are the... If I'm asking you to prove that something is a vector subspace, that means that really you have not just one thing to prove, but kind of three things to prove. What are the three things that we need to verify in order that the set is a vector subspace of Rn? So the first one is that the 0 vector... Right, so I'm going to take a step back and say what you said in a little more general way. We need to verify that 0 belongs to this set, which we can translate into a statement about what happens when you multiply the 0 vector by A. But for now, we just need to show that the 0 vector belongs to our set. What's the second thing we should show?
Closed by addition.
Closure under addition. And the third thing? Closure under multiplication by scalars. Closure under scalar multiplication. So anytime you're asked to prove something, a good place to start is to zero in on the statement that you're being asked to prove. And in this case, the statement is that this set is a vector subspace of Rn. And try to unpack the conclusion. In other words, we're trying to figure out here, how are we going to know when we've proven it? I call this the sufficient evidence. Because writing a good proof is like making a good case in a courtroom. That really what we need to do is we need to compile sufficient evidence for the statement, the claim here that's being made, to be judged true. And because of the definition, so these three things that we just wrote down came from the definition of a vector subspace. From the definition of a vector subspace, we know that these are the three things that we need to verify. And if we can verify that these three things hold, not just for a single vector, but for all vectors, for all vectors x belonging to the null space of A, then we'll have proven that the null space of A is a vector subspace of Rn. So we have to verify these things kind of one at a time. But in every case, we're going to have to keep returning back to this definition of what the null space of A is. And what is the criterion for a vector, let's say u, to belong to the null space of A? How do I know if a vector u belongs to the null space of A? What has to be true about u?
About you, is that what you said?
About u. So if I have some vector u and I'm claiming that u belongs to the null space of A, how do we know that that's true? How will we know if that's true? Say it that way. U multiplied by our matrix A should equal the 0 vector. Right. So in other words, any statement about membership in this set, we want to translate into an equation. And that equation we just got from the definition of this set in the first place. Because this set is made up of all vectors x such that, that's what the colon here means, such that A times x is equal to the 0 vector. So in other words, any statement about the membership of a vector in this set, whether it be a vector we call u, whether it be a vector we call the 0 vector, whether it be anything, that we will have proven that statement about membership if we have proven that the matrix A times our vector U is equal to the 0 vector. So let's take a moment and do that translation for every one of these three statements, starting with the 0 vector. That the 0 vector belongs to the null space of A, therefore translates to what? What will we need to verify? Here the role of U is being played by the 0 vector. That A times U is equal to 0. Right. And so U here, being the 0 vector, means that the first thing we have to verify is that when I multiply the 0 vector by my matrix A, the result is the 0 vector. So that's statement number 1. Why is that true? Right. Any matrix multiplied by the 0 vector is going to yield the 0 vector. That's actually one of the ways of understanding that is to multiply a matrix by 0 is to take a linear combination of the columns of that matrix, but every coefficient of that linear combination is 0. In other words, A times the 0 vector is going to be 0 times the first column of A, plus 0 times the second column of A, plus dot dot, plus 0 times the final column of A, and since A is m rows and n columns, that would be the nth column of A. But when I multiply any one of these columns by 0, I'm just going to get the 0 vector. So 0 vector plus 0 vector plus, and so on. I'm kind of beating a dead horse here. But just to provide some justification for how we know that whenever we multiply a matrix by the 0 vector, the result is always the 0 vector. So the first of these statements we've just verified. And so if I'm writing a proof, I might single this out as kind of step number 1 in my proof. That we've proven A times the 0 vector is equal to the 0 vector, and therefore the 0 vector belongs to the null space of A, by definition of null space of A. So this was the quick portion of this proof to show that the 0 vector belongs to the null space. It probably took the least amount of actual computation to accomplish. So let's move on to the closure under addition. Because here's where I think people started to have trouble really just getting onto paper exactly what they were trying to communicate. So what would it mean that this set is closed under addition? What do we have to prove here?
That is 2 points that you pick.
So we pick 2 points, and let's call those points U and V. And we're picking them from this set. So that's how we begin this. So we pick any 2 points, and we're making them arbitrary here because we want this to be true for all U and V. So that's the antecedent. What's the consequent? What do we have to prove about that U and V?
When added, they are also part of the null space.
When added together, their sum also belongs to the null space of A. U plus V belongs to the null space of A. So actually here we have 3 different statements about membership in this set, membership in null space of A. And so each one of those I'm going to translate. Again, using our translation machine up here, we can translate membership in the null space of A to the property of becoming 0 when we multiply by the matrix A. If I do that, that turns these into set statements, from set statements into algebraic equation statements. So if U belongs to the null space of A, what does that mean about U in equation form? What's equal to 0? A times the vector V has to equal 0. And likewise for V, A times the vector V has to equal the 0 vector. So these are the things that we're allowed to assume about two arbitrary vectors u and v that we've chosen from our set. And then what we want to show is that that membership statement also holds for u plus v. So what do we need to show here? How do I translate this statement into an equation about u plus v? If this element u plus v belongs to the null space of A, then what equation does it satisfy? What equals 0? A times that should equal 0. So this purple statement over here is the one that we want to try to prove. And the orange statements on the left are the ones that we're allowed to use in the service of that proof. In other words, the truth of these statements on the left is assumed, and the truth or falsehood of the statement on the right is unknown. That's what we need to verify. So we just need to figure out how to put the orange pieces together into the purple piece. Well, how do I do that? What's the key to this portion of the proof? Is there a way I can either put the orange pieces together or maybe take the purple equation apart in order to connect the left side and the right side here? Let's add the two orange pieces together. When I add the orange pieces together, I find out that A times u plus A times v is equal to the 0 vector plus the 0 vector. But the 0 vector is the additive identity in a vector space, so the 0 vector added to anything is itself. So when I add the two equations that we know to be true on the left, I get another equation which must be true. A times u plus A times v is equal to the 0 vector. But what does that mean? What's my final step here? We can factor out the A. And we can factor out the A because matrix multiplication is a linear operation. So it distributes over addition and it distributes over multiplication, both by other matrices and by vectors. So that means that I can factor this A out of both the u and the v terms. And now we've verified exactly the equation we set out to verify. So again, paying attention to the logic. The first thing we did was we chose a u and a v completely arbitrarily. In other words, we never said that u is a specific vector or another. We only said that u has to belong to this set, the null space of A. And likewise for v. V has to belong to the null space of A. And then we needed to prove that then their sum must belong to the null space of A. But set membership is tricky. Equations are simpler. So we translated each of those statements about membership in a set into a statement about an equation that the relevant vector has to satisfy. Namely, if u belongs to the null space of A and v belongs to the null space of A, then A times each of those vectors gives us the 0 vector. And likewise, if u plus v is going to belong to the null space of A, we need to show that A times the sum u plus v is equal to the 0 vector. And having everything in an equation form kind of gave us the roadmap to the rest of it. That just combining the two equations, A times u equals 0 and A times v equals 0 together by adding them, gave us another true equation which, when manipulating by factoring out the A, proved exactly what we set out to prove. And because we've proven that A times the sum of u and v is equal to the 0 vector, that implies that u plus v belongs to the null space of A, which is what we wanted to show. Because after all, that's what closure under addition means, is that if I choose any two elements in my set and I add them together, that their sum is also an element of that set. And the proof for scalar multiplication is completely analogous.